Hello everyone, welcome back to alkaline hydroxide 784, and today in the physics series we are going to look at the first law of thermodynamics. Yay. Okay, anyways, yeah, I do not know what else to say. Okay. So, well, I guess it seems fitting because it Singapore is hot. The thermodynamics is about heat, so seems about right. Okay, that was uh, a terrible way to start. Okay, so I'm just gonna go through the learning outcomes so that I do not say weird things like this. So, right, let's start with the heat capacity, latent heat, that kind of stuff. Like, what does that mean and things like that. Okay, so let's say you have an object and you want to heat it up, but you want to be very controlled about it. You want to heat it up by 10 degrees, like very exactly 10 degrees. How much heat do you supply to this object? Well, we do not know yet, right? Because we don't even know what object this is. Okay, let's say you were given a certain, you were allowed, you ask for a certain value to be given. What value would you ask for? Well, that would be if in this scenario you don't even know the mass of the object, so you probably ask for the heat capacity. But if you knew the mass of the object, you can ask for the specific heat capacity. So what does that mean? Well, the heat capacity of an object is the amount of thermal energy or heat that you require to bring the temperature of the object up by 1 degree Celsius or Kelvin, because Celsius and Kelvin seem to have the same step in the sense. But I think it's more appropriate to say Kelvin because everything seems to be linked to Kelvin in this, when it comes to temperature in a way. But anyways, so that's the heat capacity. And what is the specific heat capacity? That is when you divide the value by the mass of the object, then you get the specific heat capacity, like per unit mass in a sense. So if you were to tell this in words, the heat capacity is the amount of thermal energy required to increase the temperature of an object by 1 Kelvin. And if you want to look at specific heat capacity, you would say it is the amount of thermal energy per unit mass required to increase the temperature of the object by 1 Kelvin. Okay, yeah, that's pretty much it. But they don't just ask you to define heat capacity on its own. They'll probably ask you to define it with regards to a specific object or like water or something like that. Then you would have to use that in your explanation. Okay, so now you find out that the object can actually melt, but you do not know how much how much energy you need to melt the object. Basically, you want to melt it just right and not increase the temperature anymore. As you know that like melting and boiling, the temperature of the object doesn't change during the process of melting and boiling. So it is possible to supply heat energy into an object and not have it increase its temperature. So in this, so what would this heat be called? Like, what's that amount of heat energy referred as never mind. It would be called the latent heat of the object. In this scenario, it's melting, so you would call it the latent heat of fusion. If you're looking at boiling, you would call it the latent heat of vaporization. And of course, once again, specific would mean that it's per unit mass. I think I do not need to really say this out in words again. Do I? Okay. So, yeah, so that's basically what those two terms are. So heat capacity is the amount of energy to increase the temperature of the object, and latent heat is the amount of energy to melt it or to boil it without increasing the temperature. Oh yeah, when you write your definition for latent heat, please remember to say without a change in the temperature, because that is very important. That is extremely important in writing that definition. The point of melting and boiling is that the temperature does not increase. That is very important because if the temperature increases, then you're including the heat capacity as well. It's not just the latent heat anymore. Okay, so now that we completely understand those two terms, let's now move on to the next point, and we look at internal energy. Right. Last time we came up with some weird equations, or we looked at weird equations. We didn't really come up with anything, but we saw all those equations with the molecule moving around and colliding with the wall. Basically, the idea is that the energy that the molecule has is, well, is internal. The energy that all the molecules in a system have is called the internal energy. And as you can see, the molecule can move, so it has kinetic energy. And if you studied chemistry, you know that the molecules have potential energy as well between each other, like they have attractions, be it covalent, non-covalent, I don't know, your pick. And in this scenario, that means that the molecule has both kinetic and potential energy. So the internal energy of that system will be the sum of the random distribution of kinetic and potential energies of all of the molecules in the system, because the internal energy is just equals to whatever energy that the molecules actually have in the system, and that will be the kinetic and potential energy. Yeah. So what does this got to do with this entire scenario? Well, we know that the thermal energy that you add into the system will then add to the internal energy, right? Because it needs to go somewhere. It cannot just disappear into thin air or something, as we know that energy is conserved. So the thermal energy that you add into the system will then be added to the internal energy of the system. It will make the molecules go faster or something like that, because usually the potential energies will be quite constant, but they can be affected by temperature based on the scenario and things like that, but they are not that much, they don't change as much compared to kinetic energy. So in this scenario, you'll be increasing the internal energy by adding in thermal energy. And since this difference is usually somewhat proportional, so the internal energy will be somewhat proportional to temperature, as we saw last time. Yeah, that's pretty much it. There's nothing else much to say for that point. So the main thing that will be tested here is that the first law of thermodynamics, which is the delta U equals to the work done plus the heat supplied. Okay, so what is this equation? How does this relate to whatever we just told? Well, basically the delta U is basically the change in internal energy of the system. So when the system changes its internal energy, there must be a reason for it. It can't just happen on its own. So as we saw earlier, thermal energy can change the internal energy of the system, and that will be the delta Q. So if you have heat energy supplied to the system, its delta U will be positive. In other words, its internal energy will increase. And what about the work done to a system? Well, when you do certain things to a system, sometimes the kinetic energy and the potential energy of the particles will change, because when you're doing work to the system, you are actually inputting energy into the system. So like for example, if you compress the gas, you're using energy to compress the gas. So the energy will then be transferred to the gas, assuming no other losses or transfers to any other place, in the sense, if ideal energy transfer in the sense, then you would of course expect that the internal energy of the gas will increase. And that's why the the increase in internal energy is equals to the work done on the system and the heat supplied to the system. As you can see, this is very easy to remember if you think about it this way. Like, if once you do something to the system, its internal energy will increase. And it also removes the ambiguity of work done on or done by or whatever, which thing is doing work on what kind of problem, because it's very clear now. So what does work done on a system mean? Work done is usually represented by the change in the overall value of pressure times volume. So in A levels, you are usually expected to use the change in volume for your calculations. So what you would do is, you have a pressure and you would be seeing the volume change at a constant pressure, for example. Then you can use the change in volume for your work done expression. And we will see more of that later on. So that's how you find the work done. If you're looking at the heat supplied, we will then, it depends on what is written in the question or the context of the question. So from there you can find out the value of the heat supplied to the system. Okay, so let's get into the details that I wanted to talk about, which is for different contexts. So the first one will be constant pressure. That would be isobaric. If you do not know how to remember that isobaric means constant pressure, just look at the word bar, and that is one of the units for pressure. That's why it is called isobaric. Okay. So when it is isobaric, aka constant pressure, you would then have, like, your pressure won't change. But so if your volume changes, then you definitely have some work happening in the system. And from there you can calculate the work done on the system with pressure times the negative of the change in volume. Why is it negative? Okay, if in order to do work on the gas, how do you do it? You have to compress the gas, has to decrease in volume in order for you to do work on the gas. If the gas instead expands, you're not actually doing work on the gas is the one doing the work on whatever thing that's holding it down. So in that scenario, work done will be negative. And that's why when you calculate work done, you must put a negative P times the change in V, or you can say delta V. So just use that, and remember, just use the equation as normal. Delta U equals to work done plus heat supplied. Okay, so the next one will be isovolumetric, which I think is very obvious, is the volume is constant. If the volume is constant, is there work done? It is possible. If the pressure was changed, there will be work done. But in A levels, you won't really see that happening, so you can assume that there is no work done. So, like, you don't usually see a change in pressure in the scenario, or do you? I don't know. Like, the volume doesn't change. That's the point. Like, the work done, we are looking at the volume change rather than the pressure change. So the work done by a pressure change would be somewhat negligible compared to the volume change in A levels, but you might need to consider it at other places and at other times. So in this scenario, you can make your W equals to 0, and your delta U will be solely equals to the heat supplied to the system. So the third scenario will be well, the same temperature in a sense, isothermal. So I think this is also pretty obvious, isothermal, but you must not confuse this with the fourth context, which I will get to in a minute. But yeah, please remember that the isothermal is referring to temperature. So for temperature, you would you would be like, same temperature, what does that mean? Well, if it is the same temperature, that doesn't mean that the heat supply is 0. It doesn't mean that. It means instead that the internal energy is the same, because you don't need to put heat into a system to increase its temperature. Imagine if you compress a gas really fast, the temperature of the gas would increase without you having to add any heat to the gas. So do remember that in mind when you look at isothermal. Don't mistake don't put Q as 0. It's only delta U that is 0 in this scenario. So since delta U is 0, the work done and the heat supplied must cancel each other out. So in other words, the work done is equals to the negative of the heat supplied. Yeah. And the final one, which is where the heat supply is actually 0, it is called the adiabatic system. I don't know how to pronounce it correctly. Is it adiabatic or adiabatic? Never mind, it's not important. As long as you know what I'm talking about. So when the heat supply is 0, it's pretty obvious delta U equals to the work done on the system. So the isothermal and adiabatic graphs will look pretty similar. They look like some, what should I say, 1 over x kind of graph to you. So look at the question for information. Maybe the question might say no heat supply or temperature is constant or something, to make sure that you know which one it is. Don't confuse one for the other. So yeah, I think that's pretty much it. That's usually what they'll be asking you about. So you don't really have to worry about the whole, the topic that much. It's very simple. Just remember the equation, and of course if you want to remember how to write the definition of the first law of thermodynamics, it would be the change in the internal energy of the system is equals to the heat supplied to the system, the sum of the heat supplied to the system, as well as the work done on the system. I'm pretty sure there was actually some kind of there's some extra thing added to it. Yeah. I think it's about where the potential energy doesn't change or something like that. I'm not sure. But I don't think you really need to say it, hopefully. Yeah. If your school tells you to say extra stuff, then go ahead and say the extra stuff. But this is the main part of the definition, so do remember to say that. With that, I think I'm done. This is not that long of a topic, actually. There's only like 4 learning outcomes. Yeah, it's also very straightforward. It's a straightforward topic, and I hope that you do well in this topic. Good luck for your A levels if you're still watching this before your physics MCQ paper. And with that, if you found this video useful, please press the like button and subscribe. I'm asking for any feedback on my channel. If you would like to provide it, please do provide it in Word, either through the comments or in Reddit. You can PM me if you feel a bit uncomfortable to put it in the comments below. I am a friendly person and I'm prepared for any criticism. Yeah, please do give me some feedback, because I think it's important to get some feedback. Yeah. Yeah, so if you found the video useful, you can press the like button and subscribe. And with that, I would like to say thank you and bye.